All right. Well, happy Monday. And yes, so I think yesterday you should have received basically your time assignment for whether you'll take it during the morning, so this lecture at 11 a.m., or in the evening. This lecture would be assigned to 7 p.m. 7 p.m., 11 a.m. would be right here in this classroom, and then 7 p.m. would be in Kinsey Pavilion 1240B. And I will email out seating, like a map of the classroom with seat numbers and also your seat assignments, okay? And you'll figure out where you're sitting. So this classroom, I just arbitrarily kind of labeled the rows A, B, C, D through, I think, H or J in the back. And then Kinsey Pavilion, actually, those seats are already numbered. But I'll also send out a map there so you can see where they are, and I'll email those out, and that should be fine. Okay, let's take a look at today's topic. So today we are going to talk about floating point numbers, and I don't know how familiar you are with this topic of floating point numbers. Some of you have seen it before, but for I think many of you, this is kind of it hasn't been covered in great detail, and we'll actually spend 2 entire lectures on it. So we'll spend all of today on it. You'll take your midterm exam on Wednesday, and then I'll wrap up floating point numbers on Friday of this week. Okay. And again, this stuff is not covered on the midterm exam, so no worries. But it'll appear on the final, and we've got kind of two lectures on it, and so it's important because pretty much everything that we do with computers are going to be done. All the math that we do with computers are done using either integers or floating point numbers, okay? Floating point numbers are type double. R calls these things type double, but they're floating point numbers. And they are very, very different, and they behave very differently from real numbers, okay? And so, I never took like a class on real analysis. I never took Math 131A or, whatever equivalent that would be, and you can take courses on this, and you can talk about what exactly a number is and what it means to be part of the real set of real numbers, and there's different definitions and constructions for this, but kind of just at a simple intuitive level, we can kind of think of this number line, and the real number line is basically all the points on that infinitely long number line, and you've got integers on that number line, and they're all equally spaced out. But the real numbers is basically all of those points, all infinitely many of them. And you have infinitely many real numbers, and you pick any 2 spots on the real number line, like between 0 and 1, and you have infinitely many values between 0 and 1. And any 2 spots between 0 and 0.1, you've got infinitely many values. And the quote, the number of values between 0 and 0.1 is exactly identical to the number of points between 0 and 1 and things like that, which is a different infinity, right? There's different levels of infinity. You think of like your integers and your rational numbers. You have infinitely many value integers and rational numbers, but those are countably infinite, so you have the exact same number of rational numbers as you do integers, but the irrational number, everything else in the real number line, there's too many. They're uncountably infinite and stuff. But anyway, probably early on in your mathematics journey of learning math, you learn these rules: associativity, the distributive property, the commutative property, where we said, hey, you could do addition in different orders and you're going to get the same answer. You can do A plus A times B first, and then you multiply it by C later, and that's the same thing as doing B times C first and then multiplying it by A later, or something like that. And you probably taught this, I don't know, 5th grade, 6th grade, 7th grade, something around there, I don't know. And you've kind of accepted this, and this, I think, is probably ingrained deeply into your mind as far as working with numbers. Okay? But one thing is, when we deal with computer numbers, those rules fall apart. And another property of real numbers is that every real number has a decimal representation. And so you have kind of this, the decimal representation is basically something like this, 5,413.29, and in decimals, each of these positions represents a power of 10. So this 5 represents 5 of 10 to the third power, 5,000. This 4 is 4 times 10 to the second power, 400. This is 1 times 10 to the first power, 10. And this is 3 times 10 to the 0, 3 ones. This is 2 times 10 to the negative 1, so 2 tenths. And this is 9 times 10 to the negative 2, 9 100ths. And you put all of those together and you get 5,413 and 29 100ths, and so on and so forth. But a lot of the values, we can represent pretty much any value on the real number line in this decimal form. So, okay, wait, I'll get to that in a moment. Right? You take these infinite values, or not infinite values, you take these decimal numbers, and you can also use scientific notation to represent these things. So scientific notation, you turn the thing, the leading value, I guess normalized scientific notation, your leading value is not, you have one value in front of the decimal point, and it can't be a 0, right? And then it's going to be, something point something 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 times 10 to some other power, and you'll also have a sign there, things like that. That's normalized scientific notation. If it's not normalized, it's just something times 10 to the some power. So if we were to take this same number, 5,413.29, you could represent it as 541,329 times 10 to the negative 2. Now this would be a little bit of a strange way to represent this number, but it can be done, right? So this is basically saying $5,413.29 is equal to 541,329 pennies. Okay, and that's valid. Okay, normalized scientific notation. You would take this number, you would roll the decimal point, I guess 3 spots over to the left, and this would be represented as 5.41329 times 10 to the third power. So, you rolled it, because you moved the decimal place 3 points over, that means you've reduced it by a factor of 10 to the third, and so to kind of get back your original value, you have to multiply it by 10 to the third. You have to multiply this by 1,000 to get this back. And I think, we probably had to do this a lot in our different classes, especially if you took like a chemistry class or something, you were dealing with, moles and pH values, which have these very kind of very big or very small numbers and stuff. And scientific notation, again, this is what, Avogadro's number, and I think this is like the Planck something, so you can represent these very big numbers, right? How many items in a mole, which is, I think, how many atoms you need to kind of get the atomic weight of something or something, I don't know, right? So something like that. Okay, and then I don't know, this is like the smallest distance or something that we can kind of appreciate in real life. Okay, so very big numbers, very small numbers, and stuff like that. Okay, now pretty much any number, any real number, we can represent in decimal notation, and so some numbers have finite decimal representations, like the number 1/2. 1/2 is 0.5, and that is exactly equal to 1/2. Okay, And you have other irrational numbers, such as the square root of 2, or pi, or e, and these would have infinite decimal representations. Okay, even rational numbers like 1/3 would have an infinite decimal representation. It's 0.3333333, and those threes go on to infinity. Okay. But here's the thing: when we write things down on a piece of paper or store them in the computer, we cannot use infinitely many places. We cannot store all infinitely many values because we don't have infinite storage. We don't have infinite memory on our computers or infinite storage on our systems. And I mean, our computers are able to hold tons of stuff, right? You might have, 8 gigabytes, 16, 32 gigabytes of memory, and your hard drive might have like a terabyte of storage, and you can buy like an external drive, a terabyte of storage. But even that cannot be used, even if you use your entire hard drive to try to store pi, it's not going to have all of the digits of pi, right? You're going to run out of space because you need infinite storage to store the entire value of pi, and so you're only going to get trillions or quadrillions of digits, but not the full thing. And likewise, even for like the number 1/3, you can't store all of the values, right? You could dedicate your entire terabyte of storage to try to get as many decimal places of the number 1/3 as possible, and it's not going to be the full complete representation. And you would feel like that's a waste of storage, right? I need to buy a terabyte of hard drive and just to store the number 1/3 because I want all the decimal values I can possibly get, and it's just not gonna work, right? So we just cut our losses and we say, hey, you know what? Let's use a certain number of digits, maybe 10 digits, maybe 16 digits or something, and just say, hey, that's going to be good enough. That's going to be good enough, and this is going to be an approximate value of the 1/3, right? So if I write down 0.33333 on a piece of paper, let's say I use 6 digits to represent that in decimal form, it's not exactly the value 1/3. It's an approximation. And pretty much all the computers aren't able to represent this concept of the values, the decimals repeat forever, okay? That the threes keep going forever. If it's a more complicated number that they repeat and go on forever, or in some case like pi or e, there's no like shorthand to say that what's the sequence of digits that come next. There's no way to represent that, and so when you write this down and store it, it's just an approximation. And when you're dealing with approximations, there are profound consequences to it, consequences that break all of these rules that we are kind of accustomed to for existing with real numbers. Let me give you your first view quiz answer. Your first view quiz answer today is D. D as in dog. D as in dog is your first view quiz answer, D. All right, so I wrote, computers are unable to represent real numbers with infinite precision. Computers do not have infinite storage, so they use a finite number of bits to represent a number. And so this results in many numbers being represented by an approximate representation. Now, if there is a finite representation, such as 1/2 as 0.5 or 1/4 as 0.25 or something, we can do it exactly. But for everything else, it's just going to be an approximation, right? And so we'll look at the computers which store things binary in base 2 instead of base 10, but you can still see the effect of working with finite number of places with something like this. So I have this older style calculator. I mean, this calculator itself is not very old. You can still buy calculators of this model, but generally, if you have like a scientific calculator or a graphing calculator, they have basically some internal programming to make it behave a little bit smarter than a basic calculator like this. But with a basic calculator, if you've worked with this, I think you can expect some of its behaviors. So, for example, so this calculator, I can store 8 digits on the screen. I can represent 8 digits. And what will happen on the calculator if I do this operation? 10 divided by 3, and then I take that result and I multiply it by 3. So what's going to happen? When I do 10 divided by 3 on the calculator, what am I going to get? 3.33333, all right? And then when I take that and I multiply it by 3, what am I going to get? Yeah, 9. So so here I recorded a video of myself doing this. All right, so here it is. So I do 10 divided by 3. I get 3.33333. Take that, multiply by 3, and I get 9.99999. Okay? So again, so 10 divided by 3 multiplied by 3 is not 10, but 9.999. Okay. And so we get this, right? And on the other hand, if I do 10 times 3, and then I divide the result by 3, what am I going to get? Okay? Now this is, if I do 10 times 3, I'm going to get 30. And I divide by 3. This seems silly. I get 10. Okay? So that does exactly what we expect it to do. Okay? So 10 times 3 divided by 3 gives me 10. Right? Now this might not seem all that strange, but if you stop and think about it, we have broken one of the very fundamental rules in mathematics, that the order in which you do these things, this associative property of, whether I do 10 times 3 and divide by 3, or 10 divided by 3 and multiply by 3. So if we were dealing with real numbers, these two things should always be exactly the same. But when I'm working with a calculator that only has approximate representation of these numbers, these two things don't end up equal. Okay? So some of these fundamental rules that we expect break down when we're working with approximate representations of numbers. Okay? And so, some other examples you can try out, and I recorded videos of myself doing this. If you take the square root of 2 and then you square it, you don't get back 2, you get 1.99998. But if you do 2 squared, which is 4, and you take the square root of that, of course, you're going to get back 2. Okay? So these two things end up different, and they shouldn't, and things like that. Okay? And similarly, stuff like this happens in R as well. So here is, I can store 0.1 as A, and I can do B is going to be 0.3 divided by 3, right? So here's B, here's A, and I ask, is A equal to B? Right? We expect it to say yes, but when we ask R, are these two things equal to each other, R comes back and says no, they are not equal. And you go, what? Let me check A. Here's A, here's B. They both say 0.1 and 0.1, but is A equal to B? R comes back and says false. They are not equal. Okay? And I've got more of these things, right? So if I say, all right, let's just try something else out, right? If A is, we're going to store A as 0.1 plus 0.2. Okay, what's A? A looks like it's 0.3. Okay, here B is going to be 0.3. There's A. A looks like it's 0.3. B looks like it's 0.3. Is A equal to B? And we get back false. And you're like, wait, is R just broken here? And let's try D, right? So if D is, let's do 3 divided by 10. Okay, so D is 0.3. And I can say, is B, here's B is 0.3. I say, is B equal to D? That's true. But is A equal to D? No. Is A equal to B? No. What's A? A is, and we get this weird, we get this weirdness going on, okay? Because it feels like all of these things, I look up here, and they all look like they're 0.3, and some of these things are equal to each other, and other things aren't equal to each other. So what's going on, right? What's going on? So, and then here's even more examples, and I'm not even bothered. You'll just look at these things, and I say, okay, let's make a sequence of 0 to 1 by 0.4. And so the sequence goes 0, 0.1, 0.2, 0.3, 0.4. All right, sure. Okay, what's the fourth value in the sequence? That's 0.3. Is that 0.3? And so I say, okay, let's set the fourth value in the sequence to A. Let's set 0.3 to B. Is A equal to B? And it also comes back false. All right, and here's just more stuff, right? 4 divided by 5 times 3, 4/5 times 3 times 5/4. I get back 3. I have 4/5 times 3 times 5/4. And I get back 3. So here I got 3, and here I've got 3. It's not just decimal values, but is this 3 equal to this 3? And it comes back false, all right? So you could imagine the frustration of, trying to do math and trying to see if you've settled on some kind of value and if we're getting the equivalent value, and these things that, if we apply the rules of real numbers, we're expecting these things to be equal, but we're not dealing with real numbers. We're dealing with these floating point numbers, approximate representation of real numbers, and they behave very different from what we might expect, all right? You've actually encountered this already, and without probably giving it too much thought, there's probably been some kind of calculation you've done, like you ask, what's the sign of this number, right? Like, what's the sign of pi halves or something, or not pi halves, it would be the sign of pi, and you don't get back 0, you get something like 1.458 times 10 to the negative 17 or something like that. And probably somebody said, oh, it's 10 to the negative 17, so that means it's pretty much 0. So treat it like a 0. And you're like, okay, I'll just treat it like a 0. And you were okay with that. But if you think about that, like 10 to the negative 17, it's a small number, but it's certainly not 0, right? It's certainly not 0. And so, but, we just say, hey, it's pretty small, so just pretend that it's 0, right? You take the mean of some vector, right? If you calculate your residuals for a linear model, the mean of those residuals should be 0, but probably if you calculate the mean on the residuals that you've produced, you probably get something like 10 to the negative 17 or something like that. So not exactly 0, okay? All right, so here's a little bit of a clue of what's happening internally, all right? So here we can set the digits in one of the options to say, print out 20 digits or as many digits as you can are. And when you just say, hey, what is the number 0.1? We can't actually represent 0.1 exactly in binary. So in binary, when we're trying to store the number 0.1, there isn't we can't store it exactly. We have to store an approximation, and the approximation in decimal form is 0.1000001. And similarly with 0.2, we can't store it exactly. It's not exactly 0.2. It's pretty close to 0.1, it's pretty close to 0.2, but it's not exactly that. And if you do 0.1 plus 0.2, you get this, 0.3 something something ending with a 4. Whereas 0.3 is not exactly 0.3, it's 0.2999999, okay? And so this is why when we ask the computer, if we say A is equal to 0.1 plus 0.2, it's storing this as for A. And when we say B is equal to 0.3, we're getting this stored for B. And if we say is A equal to B, these two things aren't exactly equal to each other, and that's why it comes back and it says it's false, okay? But how are you supposed to know this, right? How are you supposed to know this? And the answer is you don't. You don't know, okay? Without asking for all of the decimals being represented, there's no way for you to just look at an operation and say, oh, this is going to end up with 0.29999, and this over here is going to end up 0.300004. Okay, you can't look at this and know how it's going to behave unless you've asked for all of these decimal values, right? So here's just kind of like an interesting example, right? So here I've got all of these operations that should result in exactly 0.3. I got 0.3, I got 0.4 minus 0.1, 0.5 minus 0.2, 0.6 minus 0.3, 0.7 minus 0.4. All of these should be 0.3, and under the kind of the standard printing form of R, it comes back and it says, yeah, all of these things are 0.3. But how many are actually distinct values? And there's actually 3 unique values. If I say, here I get, out of these 5, 3 of them are unique, and if I say print out all of the digits, or 20 digits as you can, we see 3 of them are 0.299999, but one of them is 0.3000 ending with a 4, and one of them is 0.2999 ending with a 3. Okay, so we have three unique values, and again, who was expecting this? Who was expecting this? So, so let's talk about how the computer stores these values in memory in kind of this binary representation, because, well, the lecture doesn't end with just everything breaks or it doesn't quite work, but it's important to know this and keep this in mind, because when you start doing computations with your computer, you have to be realistic about what you can represent and what you can do, okay? Because if you're expecting things to end up being exactly equal to each other, it's not going to happen, okay? And so you have to kind of keep in mind that all of the numbers you're working with in the computer are just approximations. Now, they look and feel like real numbers, but they're not real numbers, and you kind of run into these things, with some of these tests of equality, like 0.1 plus 0.2 is not equal to the representation of 0.3. So you have to keep in mind, and so we have some workarounds, but there's just kind of this fundamental question of, if you represent things approximately, how do you know if a certain representation is that exact representation versus the approximate representation, right? So for example, if on a piece of paper someone writes down 0.333, do they mean to write, is that an approximate representation of 1/3? Or did they actually mean to write 0.33, with a bunch of zeros after it, right? 0.33000 versus an approximation of 1/3. And if it's just, this number, there's no real way of knowing which one it was supposed to be, okay? And so there's kind of this inherent uncertainty in dealing with approximations. All right, a lot of you have seen binary numbers before, but some of you have not, and so this will just be kind of a quick refresher on binary numbers. So in decimal, every position in a number represents tens to that power. So you have tens to the 0 power in the ones place, 10 to the first power in the tens place, 10 to the second power in the hundreds place, 10 to the third power in the thousands place, and so on and so forth. In binary, everything is either a 0 or a 1, because internally in the computer, all of these transistors can either be in an on state or an off state. Okay, you have an on state or an off state. We're making progress in quantum computing now, where you can have maybe possibly more than 2 states, or I don't quite know how it works. So there might be a future where we have different ways to represent values. But right now, everything is either in an on state or an off state. So you can either have the digits 0 or 1. And with this, every value in a binary number is going to represent a power of 2. Okay, so here is, if you have 4 digits, 4 binary digits, or 4 bits, okay, then you can represent 16 unique values using 4 bits, 4 binary digits. So this first place will be 2 to the zeros, your ones place. The next position will be 2 to the ones, which will be your twos place. Next we have 2 to the 2, your fours place. And finally you have 2 to the third, your eights place. Okay, so the number 0 is 0 in all 4 bits, would be 0. The number 1 would be zeros and a 1 in the ones place. 2 would be 1 in the twos place and a 0 in the ones place. 3 would be 1 in the twos place and 1 in the ones place. So 2 plus 1 makes 3. 4, you would have a 1 in the fours place, 0 elsewhere. 5 would be 1 in the fours place and 1 in the ones place. So 4 and 1 make 5. 6 would be 1, 1, 0. 4 plus 2 plus 0, and so on and so forth. And this, you know, I don't know if you ever try to count binary on your hand, but you can count up to 31 on one hand, right? And you can count up to 1023 on two hands. You know, you can go, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on and so forth. And with a little practice, you can get quite good. Trying to do arithmetic on your hands is hard, but counting, you know, in binary, it can be done, right? So this would be 16, 17, 18, 19, so on and so forth. Is this okay? So representing all of these binary digits, and if you look at 0 through 17 and 8 through 15, it's basically exactly the same from here to here. It's just we replace the first digit, which represents the 8th place, 2 to the 3rd power, with a 1. Okay, so this is the exact column, but we're adding an 8 to every single one. And so now, you know, 1001 is 9, and 13 is 1101, or basically 8 plus 5, it makes 13. Okay, so if we kind of look down at one of these numbers, 1011, okay, we have a 1 in the ones place, a 1 in the twos place, a 0 in the fours place, and a 1 in the eights place. So if I add 8 and 0 and 2 and 1, those add up to 11. Did I give you your second answer yet? No. Okay, let me go ahead and give you your second view quiz answer. Your second view quiz answer is A. A as an apple. A as an apple is your second view quiz answer. Okay. A real number has a finite binary representation if it can only be written in in a power of 2, such as like 1/2 or 1/4 or 1/8. Those are all powers of 2. Okay, and just like you can have places after the decimal point representing you know, 10 to the negative 1, tenths place, and 10 to the negative 2 in the hundredths place, and 10 to the negative 3 in the thousandths place, you can have things after we would now call this the binary point, not the decimal point, but the binary point, okay? Because now we're dealing in binary. And so the first place after the binary point would be 2 to the negative 1, or the 1/2 place. And 2 spots after the binary point would be 2 to the negative 2, or the 1/4 place. And 3 spots after would be 2 to the negative 3, or the 1/8 place. So we would represent the value 1/2 as 0.1. Okay, in decimal that's 0.5, but in binary it's 0.1. And the value 1/4, 1/4 is 2 to the negative 2, would be 0.01. 1/8 would be 0.001, 2 to the negative 3. Okay, and you could represent something like 3/8. 3/8 would be 0.375 in decimal, but in binary, 3/8 would be 1/4 plus 1/8. 1/4 plus 1/8. So you'd have 1 in the quarter place, 1 in the eighths place, and it would be 0.011. Okay? Is that okay? So representing 3/8 in binary would be 0.011. Okay, so a lot of numbers have infinite binary representation. So just like in decimal, 1/3 has an infinite decimal representation of 0.333 with 3's going on forever. In binary, a lot of numbers will have infinite binary positions. So to get something like 0.1, 1/10 represented in binary would be 0.0001100110011, so on and so forth, off to infinity. Okay, and so we'd have to take the 0011 and repeat that infinitely many places, and again, we don't have infinite storage, so we're going to represent things approximately. We have to kind of truncate this off somewhere, and And that's why when you do some operation like 0.1 plus 0.2, is that equal to 0.3? It's just that the approximation of 0.1 plus the approximation of 0.2 is not equal to the approximation of 0.3. Those operations aren't exactly the same. So to kind of explore this, we will take a look at the IEEE 754 standard. So this is kind of the Institute of, what is it, Electrical Engineers and International something, whatever. The IEEE organization said, you know, we're going to have a standard for how we're going to represent numbers on computer chips. Prior to the standard, different computer chip manufacturers might have stored numbers differently inside of their systems and stuff, but this is now the standard, and so now all computer chips will represent floating point numbers in the same way. Okay, and so this is hardware dependent, and it doesn't matter. This is not something unique to R. So if you program something in Python or C++, and whether you're on an Intel computer, you know, your Intel chip, if you have a Mac with an Intel chip, it's going to be the same. But even your Macs with Apple Silicon, your M1 chip, and then, you know, on your cell phone you have probably an ARM-based chip or something like that, they're going to conform to this standard, and they're all going to represent numbers in the same way. And so in all of these things, if you do 0.1 plus 0.2, it's not going to be equal to 0.3. Okay? And so this standard, we're going to take a look at the original specification, which was made in 1985. It was revised in 2008, but the 1985 specification is fully contained in the 2008 revision, which allowed for, you know, kind of, I don't know, additional stuff. But and you can read more about it on the Wikipedia page. But this is, again, implemented at a hardware level, at the chip level. And so whether you are programming in R, Python, some other language, and whether you're on a Mac or a PC or some other computer, they're all going to kind of behave the same way. Okay, it's like only if you go onto a computer like made before the 1980s, right? If you're on some old relic of a thing, like kind of in this historical thing, you might have to learn how the numbers are represented there. But pretty much all of these things will be working this way. Okay, so let's think about how we would represent numbers. Like, if you think about scientific notation, what would scientific notation look like for binary numbers? Okay, so if you think about normalized scientific notation, we said, okay, before the decimal point, the number in front of the decimal point can't be a 0, right? It has to be like a 1 through a 9 or something for regular normalized scientific notation. When we're doing binary stuff, in binary stuff, we just say, well, it can't be a 0, so it has to be a 1. It has to be a 1, okay? And so in binary scientific notation, we're going to have basically a sign. Well, is it positive or negative? Then you're going to have a leading 1 followed by some bits, 0s and 1s, okay? And it's going to be multiplied, because it's in binary, it's going to be multiplied by a power of 2. You know, 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the negative 3, or something like that. Okay? And because we can always expect the leading bit in front of the binary point to be a 1, we technically don't need to store it, because that's going to be redundant to have to store. Because if it's always going to be led by a 1, you know, why bother storing that piece of information? So this is how we could represent some number, okay, like 6.375 in decimal, right? 6 and 375 thousandths in decimal, or 6 and 3/8. In binary would be represented like this. It would be, the 6 would be 110, 1 in the 4's place, 1 in the 2's place, and 0 in the 1's place. So 110 would make 6. And then the 3/8 would be 0.011. 0 in the halves place, 1 in the quarters place, and 1 in the 8's place. Right? So the quarter would be 0.25, and 8ths would be 0.125. And so this becomes 6.375. if we wanted to represent this exact same number, 6.375, in binary scientific notation, what would that look like? Okay? In binary scientific notation, we would have one digit or one bit in front of the binary point. So I would have to roll the binary point over 2 spots. Okay? So if I roll it over 2 spots, I've affected it by a factor of what? A factor of 2 to the 2. 2 to the 2. I've multiplied it by a factor of 4, basically, or I guess divided by a factor of 4. To get it back, I have to multiply by a factor of 4. So 110.011, I roll it over 2 spots, and that becomes 1.10011. Okay, 1.10011. But now I'm multiplying by 2 to the 2. And just to kind of show that this is exactly equal, this would be 1 in the ones place, which is 1. And now I have 1 in the halves place, 0 in the quarters, 0 in the eighths. I have 1 in the 16ths, and 1 in the 32nds. So 2 to the negative 4 and 2 to the negative 5. So if I add all of these up, I have 1 plus 0.5 plus 0 plus 1/16 is 0.0625, and 1/32 is 0.03125. This adds up to 1.59375, and I'm multiplying it by 2 to the 2. I'm multiplying it by 4 because I've rolled that binary point over 2 spots. And if I do this multiplied by 4, I'm going to get back the original number, 6.375 in decimal. All right, is this okay? This idea of binary scientific notation, because this is what we're going to be using when we represent numbers in floating point. Okay, so on the computer, there's technically a few standards for storing floating point numbers. Okay, so you have single precision floating point, you have double precision floating point, you also have the long double. Okay, in R, all floating point numbers are type double. Okay, double precision floating point, and that's why when you ask, what is the type of 3.3, it's going to come back as double. Okay, and that means we're using 64 bits total to store our numbers. Okay, and but with older computers where memory wasn't as abundant, we might have used only 32 bits to store some of the numbers and things like that. Okay, so so we have this. So in double precision, we have 1 for the sign to either tell if it's positive or negative. We have 11 bits for the exponent and 52 bits for the mantissa. The mantissa being kind of the stuff after the binary point, and then the exponent being 2 to the what power, right? And so here's kind of like a representation of how these bits are stored. You got 0 through 63. You got 1 for the sign, 11 for the exponent, and 52 bits for the fraction, the mantissa or the significand part. Okay. When we look at the exponent bits, we're using 11 bits. So 2 to the 11 is 2048. Okay, we can represent 2048 unique values. Half of those, we got 2 special cases. We got a special case for all zeros, a special case for all ones. All right, so that leaves us 2046 values. We want half of these, we want to be able to represent positive and negative values for the exponent. We want positive exponents, negative exponents. So we're going to dedicate half to be positive and half to be negative. So with 2046, we're going to say half of them, 1023, will be positive, and then the 1 will be a 0, and that leaves 1022 to be negative. Okay, so technically we have what's known as an exponent bias of 1023. Okay, because if I line up all of the values, if I go from 0, 0, 0 all the way to 1, 1, 1, 1, 1, I've got 2048 unique values. There's the 0 and the 2047 are reserved for special cases. So the very first number being a 1, in decimal, this actually represents 1. But what we're going to do is we're going to subtract a bias of 1023, and this is going to correspond to an exponent of negative 1022. And then the largest value that we can represent that's not special will be 111110, which is technically 2046 in decimal, but we're going to apply the exponent bias of 1023, and this will represent the number 1023. Okay, so we're basically, because we can represent basically numbers from 1 through 2046, but we're going to shift that down so that we can get some negative numbers and positive numbers. Okay, so that's what we're going to do here. So what are the special cases? The special cases are when we have all ones. That's one to use to represent infinity and not a number. And then when you have all zeros, we enter something called subnormal or denormalized mode, and I'll get into that on Friday. So just to kind of illustrate a little bit, we'll start off with a miniature version of this floating point representation. Okay, so this is going to kind of work the exact same way, except rather than dealing with 64 bits, just to keep it simple, we'll have 8 bits. 1 will be for the sign, so we can have positive and negative numbers. And 3 will be for the exponent, and 4 will be for the mantissa. So this will be a total of 8 bits. So let's think about the exponent for a bit. Okay. So for the sign, 0 if it's positive, 1 if it's negative. Okay. And one side effect is you're going to have 2 representations of 0. You got a positive 0 and a negative 0, but that's fine. We'll deal with that. It's not a big deal. Okay. But let's think about the exponent. With the exponent, we have 3 bits, so we have a total of 8 unique values. We're going to keep all zeros to be special case, all ones to be a special case. So that leaves us with 6 unique values. Okay? We want to be able to represent both positive and negative values. So we're going to say half of these will be positive, 1 will be 0, and then the other half will be negative. Now you see a little bit of the imbalance, right? We're going to have 1, 2, 3. We can represent values as big as 3 on the positive side, and we can only go to negative 2 on the negative side. Okay? You know, because one of these have to be 0, but that's okay. All right. So this is what we call a bias of 3, because 110 corresponds to a decimal value of 6, but we're going to subtract our bias of 3 to say this is going to correspond to the exponent of 3. The smallest value we can represent, that's not the special case, is 001, which is a 1 in decimal. We subtract off 3, and it's the smallest value. The most negative exponent value I can represent will be negative 2. Okay. All right, is that all right? So this is a bias of 3. And in general, if you have n bits in the exponent, then your bias is going to be 2 to the n minus 1 minus 1. Okay, I'm running out of time, but let me just do this really quickly. Let me give you your last view quiz answer, though. Last view quiz answer is E as in elephant. E as in elephant, and just forgive me for going 2 minutes over here. Okay, so for example, and then the last 4 bits are for the mantissa, right? And again, we're assuming the leading digit is always a 1. The leading bit before the binary point is always a 1. So those 4 bits will represent kind of the values after the binary point, blank, 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 blank. Okay, so this number in binary will represent the following numbers. So I've got 0 for the sign, it's a positive number, 101 for the exponent, and 0111 for the mantissa. Okay, the exponent bits are 101, the mantissa bits are 0111. Okay, so the exponent bits being 101 is a 5. I can kind of go back to this table. 101 is 5 in decimal. We're applying a bias of 3, so this corresponds to an exponent of 2. So this is going to be something times 2 to the 2. The mantissa bits are 0111. So we're filling that into this thing, 1 point, and we're going to put in 0111. Okay? And so this is going to be 1.0111 times 2 to the 2. And so this becomes 1 plus 0 halves plus 1/4 plus 1/8 plus 1/16. I'm multiplying this by 2 to the 2, so this becomes 4 plus 0. 1/4 times 4 is 1. 1/8 times 4 is 1/2. 1/16 times 4 is 1/4. So this becomes 5 3/4, 5.75. That's how it would go. Okay, I've got an example for kind of going the other way, and you can kind of see these representations. But we'll end here for today. I will see you guys on Wednesday for the midterm exam. So good luck as you study for that, and then we will continue and resume our lecture on floating point numbers on Friday. So we'll see you guys then. All right, have a good day.